Hello everybody, and welcome to a two-part series on the fiqh and the science of moon sighting. Now this is a two-part series. In the first part we shall be looking at the science of the moon and of moon sighting, and in the second part we'll go into the fiqh issues regarding moon sighting, whether it's calculated, global or a national sighting. We'll have a look at that. And it's always good to go through the science, because to understand what follows, and a basic understanding of science needs to happen also. And in this particular presentation, it's going to be graphic heavy. There's a lot of video content, there's a lot of graphical content, and I want you to show a little bit of patience, inshallah. I know the subject of astronomy is not to everybody's liking, and sometimes it can get confusing. So we've left the jargon out, we've left out a lot of the equations and everything, and we've just kept it as simple as possible, so that we can all benefit and understand and get a handle on the science, basic science of astronomy as it relates to the moon and some of what's in the heavens. And then part 2, inshallah, it'll give us a good grounding to then move on to the actual fiqh of moon sighting. Now every year it descends into a case of moon sighting on one hand and moon fighting on the other hand. So it's the moon fighting that we want to diminish and eventually end, and make it more in tune with moon sighting as it was traditionally done and understood throughout the ages, whether it was Islamic or going back into the pre-Islamic era. Until the dawn of man on this earth, man has looked towards the heavens for inspiration, and in some religions a misunderstanding also for guidance, as in the understanding of omens and eclipses. And today we know, and our religion taught us this as well, that we do not follow those kind of signs, but we certainly do look at the heavens for certain signs of impending disaster, as in the understanding of meteorites that hit the earth, comets, their flybys could be dangerous for us, and the moon and its effect on this earth. Because the moon is in a symbiotic relationship with the earth, and if it wasn't for the moon, life as we know it today would not be on this earth. And we'll have a look at that briefly, inshallah, anyway. So it behooves us to understand our closest heavenly neighbor. The huge influence exerted by the sun is evident for everybody, but people don't really understand the impact of the moon and its relationship with the earth. And it's just as important as the sun's relationship. So as I said, it behooves us to understand this, our closest heavenly neighbor, and as a result of this we then will thank our Lord when Allah subhanahu wa ta'ala says in Surah Al-Mulk, تبارك الذي بيده الملك وهو على كل شيء قدير الذي خلق الموت والحياة ليبلوكم أيكم أحسن عملا وهو العزيز الغفور الذي خلق سبع سماوات طباقا ما ترى في خلق الرحمن من تفاوت فارجع البصر هل ترى من فطور ثم رجع البصر كرتين ينقلب عليك البصر خاسئا وهو حسير. So he says, look to the heavens and look at the grandeur. You'll not find no heavenly imperfection there, and your sight will come back to you humbled. Thumma, then look again, and you will not see any flaw, and your sight will come back to you humble and fatigued. You'll tire yourself out, but you will not see any imperfection in the creation of Allah. And it will humble you, it will give you a deeper understanding, because when you look towards the horizons and at the grandeur, this creative act of Allah subhanahu wa ta'ala, and then you look within yourself and you have universes within yourself. There are huge spaces between, inside an atom, most of it's empty, right? The nucleus, and then inside the nucleus most of that space is empty. Protons, neutrons, electrons, most of their spaces are empty. The vast spaces between bits of material within you are like the spaces that you have between one planet and another planet in the external universe, right? So that's another mystery, that once you get a handle on that and get to understand that, it makes you understand and appreciate your Lord more. Because the way to understand Allah is through the manifestation of his attributes in creation to see the creative act, to understand it. So that's the reason why it's important to know the basics of the science of astronomy. It's the mother of all sciences, right? Because it gives you an understanding of creation from a top-down approach and from a down-up approach as well. And everything fits inside creation, right? Everything fits inside astronomy. So traditionally, this was something that was taught in the Muslim madrasas, madaris, and Muslims understood this science. Why? Because at the very least, it would allow them to perfect their moon sighting and their prayer times, because prayer times are also based on the rising and setting of the sun. Today we have issues regarding the 15-degree solar depression angle and the 18-degree solar depression angle. This is also because of a lack of understanding of the science of sun sighting, so to speak, in regarding prayer times, right? When is twilight? When is perpetual twilight? What are we supposed to do when you go into higher latitudes above, I think it's 44 degrees, where you start to get perpetual twilight for certain parts of the year? England will start its perpetual twilight, I think it's the 24th of May until the 24th of July, around about those dates. For 2 months, the solar disk will not descend below 18 degrees, and 18 degrees is the time for Fajr, right? So people normally have issues regarding this time on prayer times. What do they do when it comes to Salatul Isha and then Salatul Fajr? Because to have Isha, it needs to be dark, and then to have Fajr, it's the white light from the separation of the white thread from the black thread. That refers to the dawn, the breaking of dawn from the night sky. But if your sky isn't black, it's still blue, then how do you place Fajr into that night sky? How does Fajr come about? So these things they have been discussed before by the ulama for 1,000 years, but today most people unfortunately have forgotten that science. So this is the reason why it's, as mentioned, it's very important to look at the science of astronomy regarding these issues. So apologies in advance. It will be graphic intensive. There will be some videos that I will show to make people understand this. So let's have a look now. So as mentioned, it's a two-part presentation: the science of the moon and the fiqh understanding and application. We'll have a look at some case studies as well regarding this. So why study the moon? First of all, the origin and galactic history of the Earth, how the Earth was formed. To understand how the Earth was formed, we don't have a huge record left on the Earth, apart from our iron core, our liquid iron core, and a few other indications we have, craters and everything. Because our Earth was molten at one time, and because we have an atmosphere, over eons we have a complete eroding of what came before, right? So as a result, we won't be able to tell as much about our history of our Earth by looking at the Earth, but we have to look at other bodies outside. So when we look at the creators on other planets, when we look at the moon, our closest neighbor, it absorbed 80% of every single crater, every single meteorite that headed our way, asteroid, 80% of it was absorbed by the moon, which was a blessing as well from Allah subhanahu wa ta'ala. So we see the moon, because it doesn't really have an atmosphere, we see everything preserved in its natural state as it always had been. So we can glean understandings of our own Earth's evolution by looking at the moon. So this is one of the reasons why we study the moon. And the moon has an immensely important relationship with the Earth, which we will look at also. أَلَمْ تَرَوْا كَيْفَ خَلَقَ اللَّهُ سَبْعَ سَمَوَاتٍ طِبَاقًا وَجَعَلَ الْقَمَرَ فِيهِنَّ نُورًا وَجَعَلَ الشَّمْسَ سِرَاجًا. See ye not how Allah has created the 7 heavens one above another, and made the sun a light in their midst, and made the sun as a lamp. So Allah is telling you, don't you see this and the perfection of this, how the sun is a lamp. It generates its own light and shines that light towards the earth, and the moon has no light of its own, and the sun's light bounces off the moon like a mirror would bounce light, and that light comes onto the earth due to the size differences between them. So the surface of the moon is very dark. It only reflects about 7% of the light that it receives. Most of it is absorbed into the surface of the moon. So had that moon reflected 14%, our moon would be twice as bright. So when we have the white nights, the 13th, 14th and 15th, where if you were to go into the countryside, everything is a silvery glow, and it's very beautiful to look at. You can make your way, you can see your own shadow once the moon is shining down when it's full on you. So imagine if that was doubled, 14% or more. It will become brighter and brighter. So there is a hikmah, a wisdom that Allah has put in keeping that shine to 7%, just enough for us to not be disturbed by moonlight and also be able to find our way home. The moon appears 400 times fainter than the sun does in our sky. The closest the moon approaches the earth is 356,000 kilometers. So the distance between the earth and the moon is about 30 earth diameters. So it's actually quite close. So we're going to have a look at some of these numbers here, and then we will in turn look at them in more detail to understand what they mean. So the moon's orbit around the earth is elliptical, and it's 0.15% out of circular. As mentioned, it's very slightly out of the circular, and that goes almost for all of the planets, unless you have like Pluto, which is quite a bit more elliptical, and for some of its orbital path around the sun, it moves within the orbit of Neptune. So Neptune becomes the furthermost planet. When they used to classify Pluto as a planet, it's no longer classified as a planet anymore, but that's what happens. Its orbit is tilted 5% from the ecliptic. So the ecliptic is the plane of all the planets. So you have the sun, and then you have the ecliptic is the plane of all the planets. So ours is tilted 5%, so it's up 5%. So that means when it goes around the sun, when it goes around the moon, the earth, sorry, it goes in a slight tilt, and that has an impact on our eclipse cycles, which we'll look at also. So it appears 11% larger at its perigee than at apogee. Appears about 400 times fainter than the sun in the sky. Okay, so the history of the moon. When was the moon created? The moon was created alongside the earth 4.5 billion years ago, when the earth was created. We have 2 or 3 theories on what actually happened, how the moon came into existence. You can imagine that in the beginning, when everything came into existence, when Allah said, "Be, kun fayakun," and everything was, and from singularity, all material was compressed into a single singularity that Allah created, and then boom, right? It separated, and time and space were created as a result of this. Now those gases accreted into forming balls of hot mass. Those formed as they cooled rock, and then the gravitational fields, as the objects got denser, the gravitational fields became stronger, pulling in more material, and there were twice as many objects in the solar system, and due to these gravitational pulls of these objects, they all became into what we have today, the 8 planets we have today. And at some point, a large object which we named Theo crashed into the earth, and it caused a devastating impact that flung material back out into space, and over time that material, under its own gravitational pull, formed the moon. In less than 100 years, our moon was born, and it was very close. It was only 17,000 miles away, and because of that, it was revolving much faster, because the closer you are to an object, the stronger its gravitational pull. So in order for the moon to stay where it was, it needed to revolve faster, and that revolution at that time had an impact on our own day, and we look at that when we get to it. So the glancing blow to Earth gave Earth its days and nights, but it spins faster at a rate of once every 6 hours, 4 times faster than today. The collision was so powerful that it knocked the Earth off its balance into an axis of 23.5 degrees. This is the tilt that gives us our seasons. So when I mentioned to you that the moon had a huge impact on what happened to the Earth, this is the impact. So the Earth's axial tilt is 23.5 degrees, right? So it wouldn't be straight like that, it would be tilted. That's what gives us our seasons. When we revolve around the sun like this now, because at different times of the year, a different part of our hemisphere is facing the sun, we get the 4 seasons, right? So it would be spring, summer, autumn, and winter. We get equal amounts all over the world because of the axial tilt caused by that huge blow of the moon hitting the Earth. Also, the Earth was spinning faster, and our days were much shorter, and due to the proximity of the moon, it caused a slowing down of Earth's rotation that gave us a 24-hour day. In this picture, you can see this is the Earth and its axial tilt. If this is 0 degrees at the top here, its axial tilt is 23.44 degrees. So it revolves this way, anti-clockwise. The sun rises in the east and sets in the west. And it's this tilt that gives us our seasons. And this is the ecliptic. And the moon is not on the ecliptic. If it was, you'd have an eclipse, a full lunar and solar eclipse every month when when the moon would be here and the moon would be here. But because it's at an inclination of 5 degrees, it means that it either misses the ecliptic, or it's most of the time it's up here, and only sometimes it's here in its rotation around the sun, and then it's down here, right? So that's why we don't get eclipses every month. And it's also tilted slightly also. Its own tilt is 6.68 degrees. So because the moon is so close to the Earth, its gravitational pull pulls on the Earth strongest the side of which side is facing the moon. So that causes the Earth to follow the orbit of the moon. That over time, the torque generated, the Earth moved faster and faster, giving us a 24-hour day. As a result, the moon also slows down because the Earth that bulge is also having an influence on the moon. So it's causing the moon to slow down as well. And as the moon is slowing down, it's receding away from us. So at some point in the future, it will be so far away as to have no influence on what happens on the Earth, and both will become tidally locked in the future. One side of the moon's face always faces us, it's tidally locked. We'll look at the science, inshallah, in due course of why that happens. So this is tidal locking. So imagine this is the Earth here, and you have an object, this is the moon, size is not for comparison. The moon is going around the Earth. Now the moon, if its face is not always, the same face is not always showing going around the Earth. This is not tidally locked. If you look here, now you can see that the same face is always showing itself to the Earth. The far side of the moon is never visible to us because our moon is tidally locked with the Earth. And in the future, our Earth will also be tidally locked with the moon, which means that the moon will always appear as a fixed object, as an object in the sky without moving. So you'll always see the moon in one side. Now the obliquity. The moon also maintains this tilt for Earth. It helps as a global gyroscope stabilizing the Earth. If we had no moon, we would have a chaotic obliquity. So what is obliquity? So if this is the moon, this is the Earth. And remember, it's tilted at 23.4 degrees. So that tilt is important for us to have our seasons. When the northern hemisphere is closest to the sun, more of the sun's rays hit it, and it's warmer. The southern hemisphere now is away from the sun, less of the sun's rays are hitting it, and they have winter. And then 6 months later, when the moon is on this side, the northern hemisphere is away from the sun, the southern hemisphere is closest to the sun. So the southern hemisphere has summer, the northern hemisphere has winter. Now, imagine if the obliquity was like this. Now that northern hemisphere, where it should have been winter, is now also facing the sun. So it's going to have summer, right? The southern hemisphere will have summer. The other hemisphere, the northern hemisphere, will have summer as well. Now, if it was facing away from the sun, the obliquity would shake like that. You'd end up with areas receiving less sun, and if that carried on long enough, you'd have freezing weather. Like through the seasons, you'd have freezing weather, and that would have a huge impact on what life would survive in those areas. So the moon actually, with its gravity exerted on the Earth, keeps the Earth from moving too much. So that's the second huge impact that the moon has on the Earth, is it keeps the Earth within an obliquity that the Earth can manage in relation to sustaining life on Earth. So here is a picture of the axial tilt. So if our axial tilt is 20.5 degrees, right, the obliquity that is allowed for is a variance of 2 degrees. Right? So this is fine. Any more than that and we start to have problems. And this happens over a cycle of 41,000 years. So imagine you have a top. You spin the top, and the top doesn't just, the top part of the top that you spin doesn't just stay straight. It moves like this. It would move, and it also precesses also. It precesses. So the Earth, the obliquity moves, and it also precesses in a cycle that's much longer. So this particular cycle takes 41,000 years. And if the moon wasn't there, it would have swayed even more over a long duration of time. So if it swayed more than this for, say, 12,000 years, we'd have ice ages, right? Like a 10,000 year ice age. So it does a slight movement over 41,000 years, which prevents ice ages. And if we have weather patterns over eons that they cool, there's a benefit for the Earth. And then if we have weather systems over eons that where the Earth heats up, that's a correction and a balance. Allah has a balance in His creation, and it always swings between one to the other to balance each other out. So here, now we talk about the axial precession. So the axial precession is the trend in the direction of the Earth's axis of rotation relative to the fixed stars with a period of 25,000 years. Obliquity is a very slight movement this way and that way. The Earth precesses like a top, and this is a large movement now. So you see here, you have a spinning top, the Earth is also spinning. So as the top spins, it's moving in a circle over a space of time. The Earth moves, it precesses in a circle that takes 25,000 years. So this actually throws water on the astrologers and the people who believe in astrology, that when they say Venus has arisen, and if Venus enters Orion, because you were born when Orion was visible in the sky, so your destiny is linked with Orion, and when each time Venus enters Orion, you will have good luck. Or when this particular star goes through the mansion of the sky where you were born in, this is the effect it will have on your life. Or when the pole star, which is directly above, right, because the pole star is your grounding star, this is the effect you will have. But they did that through observations that meant nothing. Would those observations even hold true 10,000 years from now? The pole star would no longer be the pole star. Orion wouldn't rise where it was rising. So what would they do then when it would come to giving predictions of astrology? So this debunks the science of astrology just by looking at the Earth's precession. Here is a diagram now of what I was talking about. So the 25,000 year cycle of precession as seen from near the Earth. The current North Pole star is Polaris. Right, so here's Polaris. If you are in the northern hemisphere, if you look up, you'll tend to see Polaris close to the 0 degrees longitude. In about 8,000 years, it will be the bright star Deneb here. So 8,000 years, the Earth would have processed this, it would be. And then in about 12,000 years, it would be Vega. The Earth's rotation is not depicted to scale in this span of time. It would actually rotate over 9 million times. So this is precession. And here is, so if the Earth is on the ecliptic plane here, if this is our north, right, this is the ecliptic pole, but our north is here. So Polaris is here. And as we precess, it would move, it would face here and then face here and then go back to itself. And the same thing would happen with the southern pole as well. And here is the moon's orbit offset by 5 degrees. So barycenter, what's a barycenter? A common center of gravity. So the moon and the Earth, the moon doesn't just rotate around the Earth. They both exert a force of gravity upon each other, and they both pull upon each other. So in fact, the moon revolves around the Earth, and the Earth also feels the pull of the moon, and the common barycenter between them is about 1,000 kilometers below the surface of the Earth. So here, we have, let's have a look here. So we have an object here. So we have a binary orbital system here. So the barycenter is equal here. So this would be barycenter. Two objects are equally revolving, of equal mass, are revolving around themselves here. So if we have a second object here, now this object is larger than the smaller object. Both exert a gravitational pull. Now the orbit of this object isn't perfectly round. It's being pulled. So its barycenter would be closer to its surface. Now here, this visual will show you much more clearer. The object is very large. The second object is very small. The barycenter now is here. So the object is being pulled by the smaller object, so it's no longer stationary, and this object is in that circular motion due to this object pulling on it and keeping it in that motion. Now if we look at this object, the barycenter is here. It's moving around the barycenter. So this is orbiting around the sun, but it's moving around its barycenter, affected by this very tiny object, and this very tiny object is being sucked into the gravitational field of the last object, and it's only the rotation which is equal to the force put upon it by the gravitational pull, that is, the acceleration force is equal to the gravitational pull that is keeping it in its orbit. If it slows down slightly, it will be sucked in and destroyed. If it was to accelerate for some reason faster, it would accelerate slowly away, as the moon is doing now. So this is the what's barycenter and the Earth and Moon barycenter system. So here is a video that I'm going to show you on the Earth Moon barycenter. I'll forward that. So here you can see that the Earth is also moving, right? At apogee and perigee, it moves. So the lunar distance is approximately 400,000 kilometers, which is 250,000 miles or 1.28 light seconds. So this is the speed that light travels in a second. So this is a true to scale image here. So this is the Earth, and then this far away would be the moon, and that is the size of the moon, and that is the size of the Earth. And even at this distance, you can see that the moon is very large for a satellite of any planet. The moon's orbit is slightly elliptic. This is exaggerated. So when the moon is at its furthest away, we have the moon looks smaller, and when it's at its closest, we have what's known as a supermoon. It looks, I think it's about 12% larger. So if this is the Earth, it also has a perihelion and an aphelion, where the Earth is at its furthest distance from the Sun in its orbital path, and then it has its closest distance. And here is the moon itself with its perigee and its apogee. So here, when we have it at its closest point, this is how close it would be, thus looking larger from the Earth. And then its average position and its furthest position away from us, this is where it would be, and this is how it would look, smaller. So it's 14% larger in diameter than at apogee. So while the moon's surface luminance remains the same, because it is closer to the Earth, the luminance is about 30% brighter than at its furthest point. Here, if we look at the moon charts, these are new moons, right? So the closest the new moon will be to us on this date. In 2020, it was closest to us. The full moon happened to be before it was its closest to us. Had the full moon happened here, it would have appeared larger. But even then, that would have appeared large because it was closer than it would be here. Right? So if the full moon happened to be here, it wouldn't have been as large as it appeared here. So you can see the cycle. It carries on and on. Full moon here, at its closest approach, full moon here. And it's a cycle. And these are the new moons. So these are the dates for us. So in 2021, towards the summer, you'd have the moon at its largest, what you'd call a supermoon. And then it would retreat, and then going into 2022, from the second half, from like autumn, going into 22, it would no longer be close, but it would be far from us. So here are the perigee dates for 2011. So January, February, March, it's closest, and then it moves away in the same similar pattern here. So this is a video true to scale of the moon and sun. So notice now, depending on where the Earth is going around the sun, the Earth also has its phases. That is a full phase now. So the Earth is full on towards the sun. Now it's going through its phases, and because the moon is in the same part of the sky facing the same way, the phases of the moon and the sun are in sync. You can see here, look, here is full moon and full Earth. And then as it starts to move, you have the waning crescent here, and then we have a new moon, new Earth, if you want to call it that. So at apogee, when it's at its furthest distance from us, this is what it looks like, and at its perigee, it's closest to us, it's larger, like it's a difference of 12%, and it's visibly noticeable in the night sky. So the moon's rotation, the moon has, astronomers term it as the sidereal month and the synodic month. The sidereal month is 27 days and 7 hours, and the synodic month is 29 days, 5 hours. What do we mean by this? We'll have a look. So what's the difference between a sidereal month and a synodic month? Well, if that's the sun, and this is the Earth, and the moon, the new moon would start here, and it would take the moon 27 days to get back to the same position it was relative to the stars in the background. And that's 27 days. But the Earth would have moved in its rotation also 1/12 of the way around the sun. It would have moved this way. So the Earth would need another 2 days to get back to its position relative to the Earth, to be back in line with the sun again. Right, so where we get a new moon. So that's 29 days. So that's one lunar month or synodic month. I'll explain that in a graphic to make that more understandable. So at new moon, the moon is aligned with the sun. During the lunar month, the earth orbits revolves 30 degrees around the sun and the moon orbits 390 to align with the sun again. So it needs to, because we've moved 30 degrees, the sun, the moon, instead of moving 365 degrees, has to add another 30 degrees of movement to catch up. That extra movement of 30 degrees gives us our lunar month, the synodic month. So 30 degrees in a month, 1 degree a day. So it takes the earth 365 degrees around the sun to complete 1 solar year. So 1 degree, 30 degrees in a month. So if we were to move 1 degree a day, that would be 30 degrees in a month. So 30 times, here's the maths for it. So it works out at 4 minutes. So 4 times 360 equals 1,400 divided 24 equals 1 hour. So it gives us our 60-minute day like this. We can calculate also. So let's have a look at this visually so we understand what's really happening. So the earth travels around 30 degrees. So if this is the sun and this is the earth and this is the moon now. This is new moon, right? The dark side of the moon is facing the earth. The minute the moon moves a little bit this way, we get the crescent, right? We get the waxing crescent, which heralds the new synodic month, the Islamic month, and the new month for those who follow the lunar calendar. Now, one complete circle here is a sidereal month. If it was to complete one complete circle and get back to the same position, which is here, that is 27 days. It needs to move another 30 degrees to get back in alignment again, where the earth and the moon are in alignment to have another new moon. That's known as the synodic day. And we'll show that in a visual here, in a video. So this will make better sense to you than the way I just mentioned it. So the moon also precesses, just like the earth, the moon also precesses. There are actually 3 kinds of precession of the moon: axial precession, Absidial Precession, and lunar precession. We'll have a look at all 3 of them. So the rotational axis of the moon also undergoes precession. Since the moon's axial tilt is only 1.5, it's a very tiny tilt compared to the earth. With respect to the ecliptic, this effect is small. Once every 18.6 years, the lunar north pole describes a small circle around a point in the constellation Draco, while correspondingly the lunar south pole describes a small circle around the point in the constellation Dorado. So it precesses, but every 18 years, as opposed to the earth, which is in the thousands of years. This precesses every 18.6 years, and it completes its precession. The second one is Absidial Precession. The moon's orbit is that of the major axis of the moon's ecliptic orbit, the line of the apsides from perigee to apogee, which precesses eastwards by 360 degrees in approximately 8.85 years. So we have a second kind of precession where it's hard to explain this. You have to just understand it from here. So as it moves, it doesn't move back to the same place. It will swing a bit and move like the petals of a flower. So it actually precesses the other way. Right? It'll precess westwards, and it causes this shape. And that's a time of 8.85 years. Here is a video. This is what happens here. If you can imagine this is how the Apsidal Precession works. So after every 8 years, it goes back to what it was first. So then we have what's known as Nodal Precession. So if this was the Earth and the Moon, its 2 nodes of where it crosses the ecliptic would be here and would be here, right? So if this is the Sun and this is the Moon, and it goes like this. Now that would also precess in a period of 18.6 years, and where its shadow starts to hit the Earth is where you start to get the eclipses. So here is the Earth from the top view looking at the nodal precession over a period of 18 years. So this is how the moon's orbit would be over 18 years. And here is a side-on view. So as the orbit precesses, you can see that it's either the node is either ascending or descending, as you can see here. So it's complete, and then it starts to descend downwards. So it's ascending and then it's descending, ascending and descending. So this moves us on to what's known as the Saros cycle. So what is a Saros cycle? The Saros arises from a natural harmony between three of the moon's orbital periods. So it's synodic month, which is new moon to new moon, which is 29 days. The animalistic month, perigee to perigee, which is 27.5 days. That would be perihelion to perihelion. The draconic month, ascending node to descending node, which is 27 days. There is a natural alignment that comes every once in a while. They fit in exactly. So one Saros is equal to 223 synodic months. However, 239 animalistic months and 242 draconic months are also equal to the same period to within a couple of hours. So what that means is they line up. And when they line up, we go through like a period of eclipses starting that are going to move either ascending or descending over a very large time period, and they repeat. And they move around the Earth in a relative fixed pattern, and we look in detail at that. So before we actually look at the science of Saros cycles, let's understand what they are and how humans came to understand them. Because Saros cycles are very fascinating, and the way humans learnt about them was equally as fascinating. So it's realized by the Babylonians and even before written history. So the Babylonians followed a lunar calendar, and over time, we're talking, it must have been like 1,000 years, they realized that there is a fixed pattern in reoccurring eclipses. Now bear in mind, they couldn't verify news from other parts of the world, so they were only looking at their part of the sky. This is what makes it even more fascinating. Now they missed a lot of them, because partial eclipses in the daytime, you would never know that the moon has eclipsed the sun, because the light of the sun is so intense that it will still shine and it would be day. Even when you have like 80% or 90% coverage of the sun is still so bright that there'd be a very slight dimming, like less than a cloudy day even, and you wouldn't know. So they would totally miss that. But when there was a lunar eclipse, then obviously it would become dark. So they'd realize that there was a pattern to these lunar eclipses, right? Every so often, after a certain amount of 100 years, they would come back. So that's an incredible amount of observational skills and power that they had to realize this, because they couldn't correlate information from other parts of the world. So they made timetables. Now we have Stonehenge. The way Stonehenge is aligned in England, we have the understanding that it was also a solar calendar of the Saros cycles. There was that instrument, there was that cog that was found, pieces of cogs were found off the, I think it was the Aegean Sea or the Mediterranean, and they found that the ancient Greeks knew about this, and they've actually reassembled this device today from the remaining cog parts. They worked out what it was for, and it's like a huge feat of engineering, micro-scale engineering, to make and to understand and perfect the maths that went into that. So it's like a computer. It's literally computes. Each component computes, and it gives you the final result of what the Saros cycle is. Subhanallah. Right? So to say that the ancients didn't have astronomical knowledge like we have today is an understatement. In some instances, they were more aware of what was happening in the heavens than we are today. Why? Because we've stopped looking at the heavens. So in short, a Saros cycle describes the relationship between two eclipses with almost the same geometry, except that they are 180 degrees due west from the previous eclipse and 500 kilometers to the north or to the south, depending on that particular cycle, if it's descending or it's ascending. So eclipses that are descending are given odd numbers, and eclipses that are on a cycle that's ascending are given even numbers. So the first eclipse on a ascending cycle will start from the bottom. Remember, we had the precession of the moon's orbit from node to node. So as it starts to ascend, the first eclipse would start, the penumbra of the moon would hit the southern pole, and every year it would start to move up over time. So at some point, as the cycle rises, you'd get your first solar eclipse in the south pole, and that would carry on rising. So that same solar eclipse, full solar eclipse, would rise, and it would move it would rise 500 miles, 500 kilometers. It would move 120 degrees. Those eclipses, whether it was a partial eclipse, that partial eclipse would repeat every 18 years. That partial eclipse would repeat itself, but it would move 500 kilometers higher and 180 degrees. So where now the first partial eclipse starts in the south pole, as we are moving through the cycle, every 18 years, that eclipse, that same eclipse, would move 120 degrees. I put down here 180, it should have been 120. It would move westwards, and it would move 500 kilometers higher. So that same eclipse would be seen 18 years later in the other third of the world, 500 kilometers higher. So that cycle would slowly repeat every 18 years. And after 18, that's 54, I think, it would end up in the same place again, but it would be higher up. So at some point now, you're going to get your first your full total solar eclipse. And it would be a corresponding lunar eclipse as well, somewhere at the south pole. And that also would, your full eclipse now would move up. So every 18 years, your full solar eclipse would be 120 degrees westwards of the Earth, 500 kilometers above. So let's have a look at some visuals to explain that to us. So the extra 1/3 day displacement means that the Earth must rotate an additional 8 hours or 120 degrees with each cycle. So the calculation is 8 hours off, right? That's because the Earth needs to rotate. So this is the reason why it moves. The result is a shift of each succeeding eclipse path by 120 degrees west. Thus, a Saros series returns to approximately the same geographic region every 3 Saros periods, 54 years and 34 days, as I just mentioned. So for the next 950 years, at every Saros cycle, 18 years apart, there will be similar eclipses that will occur 300 kilometers off last eclipse and 180 degrees to the west. Okay, so it's not 500 kilometers, it's 300 kilometers. This will carry on up until 950 years, until the final eclipse at the North Pole. So this cycle carries on for almost 1,000 years. Then the final eclipse is at the North Pole, and then it starts all over again. Now this time it's going to descend. So then we get partial eclipses, because if you get your final eclipse after 900 years in the North Pole, as the moon carries on moving, you're going to start to get the penumbra of the moon will hit the Earth less and less, and you'll have partial eclipses, right? That will carry on for a couple of hundred years, and then until the whole cycle starts again. So one Saros period after an eclipse, the Sun, Moon and Earth return to approximately the same relative geometry, a near straight line, and a nearly identical eclipse will occur in what is referred to as an eclipse cycle. A Sa is 1/2 of a Saros. So half of 18 years, which is 9 years, is considered Sa. I think it's from the old Babylonian word, slightly modified by the Greeks, and then given to us. So here we can have a look at a Saros cycle. So here is the it's descending, right? So it's moving around the Earth. Now the nodes are where it intersects with here, look. So here's a node and there is a node. But look what's happening now. It's descending. This ascends and this descends. So if I forward this, there, you see now? And if we carry on, there you go, look. So this is now descended and that side has ascended. This is your 18-year cycle. And then it starts to move back again. So in 1999, we had an eclipse, which was eclipse 21 of 77 in this current Saros cycle. 5th of 41 total eclipses. 2007 total in the USA. I think that's 2017. I made a mistake here. So in 1999, for those of you who are old enough, you'll remember that in England we had an eclipse. There was a great hoo-ha about this eclipse because it was, I think, 98% coverage. Most people were expecting it to become completely dark, but that 2% of that sun that stuck out from behind the disk of the moon gave enough sunlight that nothing much really changed. It may have just dimmed slightly. I remember observing that eclipse. Now, 18 years later, in 2017, exactly 120 degrees due west and 300 kilometers up, there was another eclipse that we had in America, which was a total eclipse. And that was the next follow-on. So 18 years later, after 2017, that same eclipse will happen on the other side of the world, and then another 18 years later it will happen again back where it started. So it travels every 18 years around the globe, and as it works its way up. So its last total eclipse of this cycle will be in the year 2648. The last partial eclipse will be in the year 3009, then the cycle will end. So this carries on for thousands of years. And the Babylonians worked this out just by mere observations, without any correlation of information from different parts of the world. Here we're looking at a Saros cycle that's to do with the moon. So remember, we have eclipses, solar eclipses, and then we'd have lunar eclipses that would follow patterns that would be on average 6 months apart. So if the moon, as it's going around the earth, being obscured by the penumbra of the earth here in its orbital path at the top of the Saros cycle, it would miss the shadow of the earth, so you'd have no eclipse. As it moves down now and it's caught into the penumbra, you start to get partial eclipses of the moon. As it moves down its cycle and it's now in the umbral stage, you have a complete total lunar eclipse. Now this makes the moon red because of the way the light of the earth is scattered. And then it stays as a full eclipse, and then it starts to move out of the cycle. It will be partial, penumbral, and then no eclipse here. This is a descending node lunar eclipse path. So here is a map visually illustrating what I mentioned. So in 1937, you had an eclipse here. Exactly 18 years later, in 1955, 120 degrees west, the eclipse would start here and move in a path like this and end here. Then exactly 18 years later, 18 years and some months, in 120 degrees westwards, which is the other side of the world now, it would start here and it would finish here. Right, so, and then we'd go back here and it would start again. And then start again, and then again, so on and so forth. So it goes around the world. So here is a table describing the eclipse. So we have about 40 eclipses in one Saros cycle. The dates match. So if this is the old Saros cycle and this is the new Saros cycle, look, in 1997, in March, we had a total eclipse and then a total eclipse. And in the new cycle, you'd have around about the same date, a total eclipse and a total eclipse. Partial, partial. Right? The data matches. So these are the cycles that repeat themselves. So there are between 2 and 5 solar eclipses each year, with a total eclipse taking place every 18 months or so. Total solar eclipses are seen every 400 years from any one place on the surface of the Earth. While rare, the maximum number of eclipses that can take place in a calendar year is 7. Tropical year is 364 days. The eclipse year is 346 days. So this is how we get the precession. 90 days shorter due to precession with an E of the Earth-Moon system. During this 18-year period, about 40 other solar and lunar eclipses take place, but with a somewhat different geometry. An eclipse season features an approximate 35-day period during which it's inevitable for at least 2 and possibly 3 eclipses to occur. Typically, there are 2 eclipses in one eclipse season and 2 eclipse seasons in one calendar year. The eclipse seasons repeat in cycles of 173 days. which is approximately half a year. The middle of the last eclipse season was December 11, 2020, presenting a penumbral eclipse of the moon on November 30, 2020, and a total eclipse of the sun on December 14, 2020. So after a given lunar or solar eclipse, after 9 years and 5.5 days, which is half a Saros, an eclipse will occur that is lunar instead of solar, or vice versa with similar properties. For example, if the moon's penumbra partially covers the southern limb of the earth during a solar eclipse, 9 years and 5.5 days later, a lunar eclipse will occur in which the moon is partially covered by the southern limb of the earth's penumbra. Likewise, 9 years and 5.5 days later, after a total solar eclipse, on an annular solar eclipse occurs, a total lunar eclipse will also occur. This 9-year period is referred to as a SAR. It includes 111.5 synodic months, or 111 synodic months plus 1 fortnight. The fortnight accounts for the alteration between solar and lunar eclipses. So when I showed you the chart with the data, you can see this happening there in that chart. So here you can see the eclipses that occur and the corresponding data, whether it's an annular eclipse or a total eclipse. So here we can see the number of eclipses here, the total eclipses and the annular eclipses, and this is the path it follows due to the moon's own rotation and then the earth's own rotation. The reason these lines are obscured is because we cannot spread out a map evenly. If you were trying to open up a globe and spread it out as a map, it would become like this. That's the reason why Antarctica is showing as the hugest country when it's not. It's like here. And Greenland always shows huge on maps when Greenland is actually really quite small. It's only because when you spread out a map, so that's the reason why you get this distortion here. For those who want to follow Saros cycles and eclipse seasons, this is how they work. It takes some understanding, but this is how a Saros cycle moves through huge expanses of time, like hundreds of years. And then it finishes, and then it starts from the bottom, starts working its way up again. And then it moves up. And an ultimate finish. So the lunar month is the period it takes the moon to go through all the moon phases from a new moon to the next, and it lasts on average 29.5 days. This is 5 days less than an eclipse season. Therefore, there will always be at least one new moon resulting in a solar eclipse and at least one full moon resulting in a lunar eclipse during each eclipse season. This is also why solar and lunar eclipses come in pairs. A solar eclipse always takes place either about 2 weeks before or after a lunar eclipse, and vice versa. At most, there can be 2 new moons and 1 full moon, or 2 full moons and 1 new moon in the same eclipse season. So the regression of nodes.
In this video, we're going to take a look at the regression of nodes. Here we see the Sun, the Earth, and the Earth's orbit. Next, we're going to put on the ecliptic plane. And finally, let's put on the Moon's orbit and tip it 5.1 degrees. The Moon's orbit's tipped out of the ecliptic plane. Now, if all of this is not confusing enough, it gets worse. The Moon's orbit spins in a circle. We call it the regression of nodes. Here's why. The line you see going through the middle is where the Moon's orbit intersects with the ecliptic. It's called the line of nodes. And that line spins because the Moon's orbit is spinning. Not just the Moon, its orbit is spinning. Now, because of this, it changes when we have eclipses. We should have them every 6 months. Instead, they're off by a little bit every year.
So libration. What is libration? Libration is the wobble of the Earth as it revolves around the Earth in its synodic month. Let's have a look at this video to give us a better understanding. Okay, so I'll explain everything one by one. So here, if we look at the Moon, you can see that the Moon is wobbling. This is its monthly, so this is the Moon phase, and it's moving around the Earth in a month. So as it moves around the Earth, you can see that it wobbles, right? So it'll wobble this way, and then it'll wobble back, and then it will wobble back the same way again. Now, the reason for that wobble is So as the moon revolves around the sun, here's the moon revolving around the sun. As the moon, revolves around the earth, you can see here that because the moon is tidally locked with the earth, the same face will constantly face the earth. This is the same face. We never get to see the reverse side, the dark side of the moon, as they call it. We never get to see the dark side of the moon because it never faces us. We are tidally locked, the moon's tidally locked with us, and we only see this face. And that's because the moon exerts a gravitational influence upon the earth that causes a tidal bulge. We get tides, and those tides bulge out here. So the gravitational pull of the earth on the moon is strongest here and weakest here. So that causes the tides, and our moon is tidally locked with the earth, but the moon slightly moves faster than the tides. Why is that? Because the tides have a lot of friction and torque in the way. There's continents, there's other things happening on earth, the continental shelves, that slow the movement of the tides. So what happens is as the moon gets slightly ahead of itself, it has to then correct itself, right? So that's the corrections that you see are the moon's face wobbling like that. Now if we have a look here, these are the phases of the moon, and you will see that if the sun is here, the sun is shining full on towards the moon. Now here we have full moon. The sun is shining equally on the surface of the moon and the earth here. So we have full moon here. So if we look down here, this is the date, 27th of January 2021. And here 99.4% of the moon surface is visible. If I were to just click and click again, I'd probably make that to 100%. Now that's a 14-day-old moon, which is half of the synodic month of 28 days or 29 days. This is a full moon here. This is the diameter. This is the distance from us. So it's 30.16 Earths away from us. And that's its position in the sky. And these are things that we don't need to concern ourselves with. So here, as we now move, you can see that right, I've gone ahead of myself. The video ended. So as we now proceed, you can see that this is full moon, here is full moon. Now here are the faces of the moon. So now, if we are observing the moon from this angle in its monthly cycle around the earth, we can see that the crescent is now waning. It's getting shorter and shorter, the dark. So we can see now that the crescent is now waning and it's getting smaller and smaller. There, you can see that corresponding here. So now here is the dying moon. It's only 3% visible. This is the dying, waning crescent. And the new moon would be right, the moon's growing again now. So here is the new moon. So you can see this is, we call it dark moon because it's not visible. It's still there, but here is the sun would be here because you can see the sun is shining fully onto the surface of the earth, and the moon is in between the sun. So the moon now is invisible because this side of the moon is receiving the sun's radiation, rays, and this side is not. So we don't see it. But as it moves a few degrees from our line of sight, it moves back into a position where the phases start to appear due to its relative position between the Earth, Sun. And here you can see this would be the new moon. It's only 0.5%. It's less than a day old. It's only 11 hours old, right? And we'll be looking at when it's possible to see the new moon when we look at the thick part of this presentation. So I'll just play that again. So here is the libration. So as it's going around the Earth, here is, and then it wobbles. So due to the libration, we get to see slightly more we see more than 50% of the moon. Why? Because as it wobbles before it corrects itself, we get to see parts of the moon that would otherwise not be visible had it not wobbled. So when it wobbles one way, we get to see more, and then when it corrects itself the other way, we get to see the other side of it as well. So this is the libration if we take out everything else. It's a beautiful sight. So this is your 28-day, 29-day moon cycle, new moon. And then full moon. And then new moon again. Here's some fun facts now, moving away for a second from boring moon science. The moon has approximately 300,000 craters, right? I've made spelling mistakes here, between half mile and some of them to over 500 miles in diameter. Now, when we look at the moon and we see the face of the man on the moon, which they call the man on the moon, these are actually huge craters, and some of the impacts were so severe that it literally cracked the surface of the moon, the crust of the moon, and it exposed lava. And those lava fields, the lava spewed out for hundreds of miles, covering those craters. That's why we have what's known as the lava sea of serenity, sea of tranquility, sea of fertility, sea of nectar. These are huge lava fields. And some of them, like this one here, the largest one, the Imbrium Basin, is 700 miles across. And the craters cover 80% of the surface of the moon. So this tells us that in the past, our Earth also suffered huge crater-asteroid impact that created craters. And there are still, some of them are still visible, the one in Arizona, some of them are still visible today. But it's because of the effect of the weather, we no longer see them because everything gets eroded. And geologic activity on the Earth was different than what it was on the moon. So a lot of these signs get worn out over centuries. So now moving on to tides. Tides are formed on the Earth due to the gravitational pull of the moon and the sun. So the moon's gravity actually pulls upon the crust of the Earth, and it pulls on the oceans. But because of the oceans are less dense, water is less dense than rock, the Earth doesn't really have a bulge as such, but the oceans do have a bulge. So we have what's known as a tidal bulge. Now the tidal bulge stays exactly where it is in reference to its face facing the pull of the moon. The Earth basically moves through it. So as you move through the tidal bulge, you see a high tide, and then as you pass it, you see a low tide again. And then we have one on the opposite side of the Earth as well, and then that's why we have one twice a day, because you will then 12 hours later move into the bulge on the opposite side. So here we have low tide and high tide taken from the same place at different times of the day, and you can see a significant difference, right? That's like probably 12 foot down. And then during high tide, it comes up to here. So the water kind of comes up here. So the tide is way out now, way out. And as the moon moves, as the Earth moves into the bulge, the tidal bulge, it will fill up again. This is an animation, so we can see that if this is the moon, and here is your 24-hour day, we have one bulge facing the moon, and we have an opposite bulge. Now, we can understand why this faces the moon, because the moon's gravitational pull is strongest on this side, so it tends to pull the water. Why do we have a bulge here? The reason we have a bulge here is because the Earth has a gravitational pull that is pulling the water in on itself. Now, the moon has a gravitational pull that's pulling the water this way. But the Earth carries on pulling the water down on all sides. And the downward pull of the Earth squeezes because this is being pulled out this way, there's not much here because the Earth is pulling equally on all sides. But because this has been pulled by the moon, there's less water here now and it's being pushed out. But the Earth is still pushing down everywhere. But because of less water being here, naturally you're going to get a bulge that forms here. It gets squeezed, because if it's being squeezed down, and it's also being squeezed here, but it's equally being squeezed everywhere. So as it's squeezed down here and here, it tends to push it out here. and this is because of the tidal bulge. So here's a video explaining how tides work. So here you have high tide, and then 12 hours later, you'd get another high tide here when it's facing the moon. So what are spring tides? Spring tides and neap tides is to do with the Earth, the moon, Earth and sun. They call it zyzzy when three bodies are in alignment. So here we get a high tide. Because the moon is in line with the sun, we get a very high tide. And then here you'd get an extremely low tide. If the moon was here, the tidal effect of the moon was here, the tidal effect would be different. It would cancel out the pull, because the sun also pulls on the Earth, right? The sun exerts a gravitational pull that would be more greater here than it would be here. And it can also displace water. And because the moon also displaces water, if the moon was here, it would cancel out the effect, or if the moon was in another part of the sky. So here we can see the combined gravitational pull of the moon and the sun. So we get extremely high tides, and then you'd get extremely low tide here. Then if the moon was here, we'd have a neap tide. So we'd have a low tide here now, because the sun's gravitational pull is less than the moon's on the tides, because the moon is closer. So the moon would be pulling most of it. So you'd get a low tide here and a high tide here. Allah says, Bismillah ar-Rahman ar-Rahim, يَسْأَلُونَكَ عَنِ الْهِلَّةِ قُلْ هِيَ مَوَاقِتُ لِلنَّاسِ وَالْحَجِّ. So Allah says, they ask you about the crescent moons. Say they are a means to measure your specific times and are also for the commencement of Hajj. The way to understand this is that creation, everything in creation moves in circular motions. We just saw the circular motion of the orbit of the Earth, the orbit of the moon, the 24-hour rotational orbits of the Earth and the moon. The sun itself is moving around the galaxy. Galaxies itself move around centers of gravities of millions of other galaxies around a common center of gravity, which are themselves moving in other clusters of millions and billions of other galaxies, which are then separated by vast distances, and then you have other galaxies part of other superclusters. And everything is cyclic. Time is cyclic. You are born as a child, and you get stronger and taller. You reach your zenith, and then it's your nadir. You start to come down again, and you die pretty much like a child again, helpless. So we don't have a concept of just moving forward without any reference point. Our idea of time is that we don't just move through time without any reference point to anything else. We have an understanding that cycles repeat. We have an understanding that there is a beginning point for that cycle and an ending point for that cycle. And that's how we organize our days. So we cycle through our 24-hour day by repeat forms of worship, like we pray 5 times a day. That's done every day. And that's the basic framework for our day. And then within that framework, we pepper those gaps with other forms of worship. And we basically go through life with those forms of worship that repeat, but we just increase on them. So we're moving forward in a cyclic motion. So we're increasing everything we do, but it's the same act done again and again. So qualitative wise, it improves, but the actual time duration on the act stays the same. Or you can increase the time duration as well, but it all amounts to the same thing. It's the cyclic nature of what we do. And creation also shows marks of a cyclic nature in everything. Even within us, the universe within us, right? We have protons, electrons moving around our atom. Like in our weather systems, we have cyclones, typhoons, hurricanes. They revolve around a common core, a common center. The heart, which is the center of your being, is in the center, and we basically revolve around our ego, our heart. You can either revolve around your base ego, or you can revolve around the illuminated heart that is attached with Allah. And if you revolve around the illuminated heart that's attached with Allah, you're moving upwards to Allah in the right way. But if you revolve around your base heart, your ego, you're descending away from Allah into your more bestial nature. So you're moving in the wrong direction. So the ancients knew about this, and they revolved, their whole year was fixed. Because today we have the luxury of living in air-conditioned houses with cold when we need it and hot heat when we need it. And it detaches ourselves from what's happening around us in the heavens and on the earth. Because by looking at the signs of creation, do you see the signs of Allah's creative act? So by looking at creation, everything in creation points towards Allah. So by looking at creation and following the cyclic patterns of creation, you will forever be orientated towards Allah. And indeed, if you look at creation, Allah says this in the Quran as well, right? Look at the signs of Allah in the heavens and the earth. So when you look towards creation, you'll find patterns that will enable you to live in a very natural way, in cue and in timing and in sync with everything. And to be successful, if creation is left on its own, it's successful. It will survive. Those checks and balances put in place in creation ensure that it corrects itself without outside interference from man. When man starts to meddle with the patterns of Allah, we have problems like global warming, and we have these problems that we have in this world today. And when you start to meddle with your own cycle, because we have circadian rhythms, right, within your body, 24-hour rhythms within your body. If you mess with those, i.e. you don't eat the correct things, there's a balance, right? Hot foods in cold climes when it's cold foods in hot climes when it's hot. And then if you're sick, your body's hot, you need to measure it with cooling foods or medicine. When you're cold, you measure it with hot foods and hot medicine. When you need to sleep, at nighttime creation sleeps. You have circadian rhythms that fit in with those those 24-hour cycle patterns. So you honor your body by doing what you need to do at nighttime and getting up early with the sun. When the sun comes up, you get up. When the sun goes down, it's a time for rest. Allah created the sky as a blanket for you at night times to rest you, to give you rest. And then when the day comes, it's day for work. So the ancients knew this, and they worked along these cycles, and they lived happy, right? So they prepared for the coming cycles. They were constantly in tune with Allah by looking at His creation. So they were people who lived with their hearts constantly attached to Allah subhanahu wa ta'ala and constantly aware. They weren't mughafil, they weren't heedless. Unfortunately today, because we've forgotten these cycles, we cannot even see stars in the sky due to light pollution. So we don't know what's happening in the cosmos. We can't see the relationship between the stars, the moon, the sun, and ourselves anymore. We don't have gardens. We don't walk into the countrysides. We don't spend time in nature looking at flowers, looking at the leaves as they bud through the seasons, the changes in the seasons. Like it's spring now. In the springtime, you have the weather's very temperamental, right? In one day, the heavens are very loud. They're coming alive again. They're very noisy. You'll see the weather change 10 times. You'll get a cool blast. You'll get hail. It will rain. The sun will come out. This is the weather. This is the cycle, the rebirth of the year. It's waking up, and it's adjusting and setting itself for the summer ahead, when everything will grow again. And then you have the harvest time, when you reap what you sow. And in the winter months, the twilight years of your life, the twilight of the year, you live off what you sowed, what you reaped. So man also lives the same way. He has his youth, he has his middle age, he has his twilight years. And what he did will determine how he'll get through it. Right? With the famous story of the ant and the skylark. Skylark singing away, wasting his summer. The ant vigilantly working. When it comes to the winter, the bird starved, whereas the ant survived. And then there is the teamwork involved inside there. So we have our relations, and it all builds upon, everything is built. So just following nature, outside, external, and within yourself, will make you live in that same way. So to observe nature is something that we don't do. Just to have a plant that you observe the whole year, whereby you plant the seed and then you see it grow. You see it change with the seasons. You see it flower. You see it seed, and then you see it die. That will give you a powerful perspective of yourself and what you're doing here in this world. And it sets you in a course of where you then divide your year, your months, and your days into cycles of worship and work and rest and family. So the ancients lived by the moon. They would see the heavenly objects, the growing of the moon, the waxing, the waning of the moon, the repeat, like once a year as we move through the seasons, certain stars would rise and set at different times of the day, and the horizons would constantly change, because nothing is stationary, and everything needs change, everything changes. Only Allah is, and everything else is perishing, it moves. So moving from one state to another state is a perishing of the previous state, and then the creation of a new state, and then that new state would also perish. Another cycle. So by following these patterns, they set their internal clocks, their external clocks, their lives. So they had a profound understanding of the way nature worked, and they needed to, because they didn't have the luxury of fortified cities or strong buildings. They were open to attack from animals. They were open to attack from pestilence and pandemics. They were open to attack from the seasons, the weather. They didn't have defense against the weather. So they would read these signs and interpret these signs and plan and live and be cautious. Just as a Muslim, his whole life is one of planning and being cautious of sin. And anything that harms you, right, you plan for that attack. You know what the harm is and you avoid it, just like they would know what certain weather signs would mean, how it would harm them. So they would avoid it. They would plan time avoiding it so they wouldn't suffer. So we see these cycles in creation, we take from them and we move forward, because all creation is moving. Nothing is stagnant, and all creation is changing. Even those repeat cycles over thousands upon thousands of years, they also change. And certain stars that were documented to have risen in certain parts of the sky in the medieval period no longer rise in that. Why? A, due to precession. B, they themselves are moving also. Like the tens of light years away or the hundreds of light years away those stars are at, they're also moving as well. So man shouldn't be stagnant. Man should also move, and move with the seasons, and move. If you are a weak Muslim and you can't find direction, observe nature and move with nature. Nature's on a journey back to God. Just follow the footsteps of nature, it will get you there. Mother Nature will get you there. So the ancients, they demarcated their months with the lunar calendar. Some use the solar, most use the lunar, and when we look at intercalation, we will discuss the calendars, the lunar calendar, the solar calendar, and how sometimes they have the lunar solar calendar. That's an additional lecture, inshallah, that I'll give. That's not part of this particular course. That's interesting to look at as well. So when the ancients set their monthly cycles based on the moon, because it was very easy to observe the waxing, waning moon and then demarcate your month like that. So they would see patterns in nature also. So they would call those moons by what they observed in nature. So it's a very charming way to give nature these names. It's like when you see flowers and when the flowers burst into bloom, right? There are very charming names of how you can observe those flowers, and you know they are showing forth their finery. They are draped in their finery. They are chattering with each other as they move, and then the bees dance in between. And then when you get like the heavens, a tempest in the heavens, the heavens are fighting. You can literally feel that. You can actually feel nature speaking to you. Just observing nature at certain times of the year, you can actually feel like nature is having a conversation with you, and it's interpreting those signs that you get deeper understandings of your Lord. You can actually observe nature and see what Allah is saying to you. So let's have a look at what they named the moon. So January was called the wolf moon. The full moon in January is the wolf moon, named after howling wolves, which may stem from the Anglo-Saxon lunar calendar. Other names was the moon after Yule, which was New Year, the old moon, ice moon, and snow moon. Why would they call it that? Wolf moon, because in the dead silence of the long nights in the winter months, you'd hear the wolves howling for longer than you would during the summer months, when you'd have other like sounds of nature drowning out the sounds of the wolves. The moon after Yule, because of the shortest day of the year, you know, the festival, and then the days start to get longer. You have the old moon, because it's the old moon now. After this is the new moon. Ice moon, because it's the winter month, and the snow moon. Such charming names. In February, they'd again call it the snow moon. The snow moon is the full moon in February, named after the snowy conditions. Some North African tribes named it the hunger moon due to the scarce food sources during midwinter, while other names such as storm moon and chas moon, but the last name is more common for the full moon in March. So the worm moon, right? March now you start to get the earliest flowers budding and earthworms coming up, and then a bit of food available for birds. So they'd call it the worm moon. And the crow moon or the cross moon, the sap moon, the sugar moon, the chas moon, the lenten moon. In April you'd call it the pink moon. Why? Because then in April you'd have like, you know, the early flowers like the tulips and daffodils that grow in this month, and those are the colors of those flowers. And you'd call it the pink moon, right? You call it sprouting grass moon because grass would start to grow. Fish moon, hare moon, egg moon even, and the pasture moon, because it used to calculate the date for Easter. That's fixed to the date of Easter. So fixing your moon names with what's happening in the earth is a powerful reminder of what's actually going on around you, as opposed to saying, oh yeah, it's the new moon. Oh, it's the new moon. Every month, oh, it's the new moon. But if someone said it's the pink moon, it immediately brings you back to reality. This is the time now where the flowers are coming out. So we will have more food. This is the time when we need to start sowing the ground and planting seeds. And it's just a very romantic, charming title, Pink Moon. It kind of conjures up images of meadows full of flowers and warm nights and buzzing bees and things like that. It just makes life more enjoyable, more organic instead of sterile. So May is the flower moon, to signify the flowers that bloom during this month, the corn planting moon and the milk moon from the old English Anglo-Saxon. June, strawberry moon. Some berries will start to ripen now. Hot moon, mead moon, rose moon. In July you'd have the buck moon, because the new antlers that would emerge on the deer's foreheads. The thunder moon, wart moon, hay moon from the Anglo-Saxon. August is the sturgeon moon. This is the fishing season. Larger number of fish in the lakes where the Algonquin tribes fish. This is in Canada. Then you had the green corn moon, barley moon, fruit moon, grain moon. These obviously point towards certain things that were happening in those months. September, the harvest moon. This is the time where you start to harvest now, right? The equinox is September 22nd. This is now where your day and night is of equal length. Now the days will start to shorten and the nights will lengthen. Corn moon again, harvest moon. Then the hunter's moon. Every 3 years the hunter's moon is also the harvest moon. Traditionally people in the northern hemisphere were preparing for the coming winter by hunting, slaughtering and preserving meat. So this is when you cure meat with salt. You dry meat, you leave it to dry so that in the winter months, because there were no refrigerators back then, you'd have to cure it, and it would last you through the winter once, but you'd have to make it into broths and brews by water and adding other things in there that you could get hold of, and that's how you would survive. Beaver moon, again, is something to do with the beavers. I think this is the time when they make their dams. So if you'd want to hunt them, you'd go and hunt in the areas where they would be making their dams during this month. And it's the last full moon before the winter solstice, which is the shortest day of the year, which would be the 21st of December. And then after, then the days start to get longer again. It's also called the morning moon because it's the last moon of the year. If you're going to base this as like the lunar solar calendar, this is going to be the last moon of that particular solar year. December, the cold moon, nothing happens, the world rests. It's a time of rest for the earth, and it's all silent. It's known as the cold moon. Crystal clear skies, you just see the moon in all its glory, and there's the dark sky, no vegetation, everything is dark, the earth is dark or blanketed with snow, and it's just snow, dark sky and silver moon, the cold moon. Also the wolf moon and the moon before Yule. Supermoon is, as mentioned, when the moon is at its closest to the earth in its orbital plane, and it's larger than another moon, and we call it supermoon. The Perigean full moon. Harvest moon. Okay, dating back to pre-industrial times, the harvest moon refers to the full moon that occurs closest to the start of autumn, when farmers would start the harvest. So farmers needed extra light. When you harvest is an activity that the whole village would join. Traditional villages were mostly composed of 1 or 2 or 3 families, extended families. So you maybe have like 50 members or less, or maybe even up to 100 members, but they would all be blood related, close or far. And their fields would be around the village, and during harvest time you have a very short season because the drying hay needs to be harvested and taken indoors. Crops need to be picked or they will spoil, and the rain can spoil certain crops, certain flowers, and the hay as well. So this is a collective venture where the whole village, men, women and children, would get together and help one family harvest as quick as they can, then help the other family, then help the other family. And it was a joyous time bringing together everybody. It was teaching them teamwork and skills of caring and helping, and basically helping each other to survive. Today, where we've forgotten to do that, and it's kullu wahid nafsi nafsi, everybody for themselves. Whereas then it wasn't for themselves. It would be more about the other person, less about yourself. Because if everybody was caring about the other person, then all society would be sound and everybody would be taken care of. Whereas if it's everybody for themselves, there will always be people marginalized. And in a village, you'll have the successful farmer, the lord of the manor, and then you would have the poor tenant farmer. He would probably be a cousin, but would be tenanted to work on the farms of the squire, the lord of the manor. So he would be taken care of. He would not be taken care of if everybody was concerned about themselves. He only gets his lot because everybody's sharing and caring for themselves. There was no medicine or doctors, or everything was self-contained in those villages. So it was a very joyous time for everybody to get together during that period. Blood moon. Now a blood moon, and yes, this is a real picture of a blood moon. If you've ever seen a lunar eclipse, a full lunar eclipse, when the moon is within the Earth's umbra, not the penumbra, the umbra. Due to the atmospheric refraction of light rays, it filters out, it absorbs the blue and it scatters the red, and it's only the red rays that get to hit the moon that gives it the blood red glow, and it's called the blood moon. Blue moon, that's another word. It's a rare event. It's when you get two full moons in the same month. So it happens every 2.5 years. Once in a blue moon. The idiom once in a blue moon comes from there. Means a rare occurrence. So now we look at moon phases. We move on to moon phases. Now these are the phases of the moon. So that's new moon here. Now you can see the full moon here, right? You can see the full moon, and the new crescent is brighter than the full moon. The reason for this is earth glow. The earth also reflects light back onto the moon, so you get to see the outline of the moon here. This is the sun's light. We'll have a look at how this works in other slides, inshallah. So this is the waxing crescent as it grows larger and larger. Here's full moon, half moon. This is quarter from our vantage point on earth. This would be a quarter of the way around, and then it's gibbous, waxing gibbous, and it grows into a full moon, and then it starts to wane. This would be approximately 14 days of its orbital period. And then here, once this finishes, we have another moon here, which is known as the dark moon or the new moon, and then the cycle repeats again. So this is the new moon. It's dark. This is called a young moon. The waxing crescent, the waxing gibbous, full, waning gibbous, waning quarter, waning crescent, and the old moon, and then followed by new moon again. So this is how they work. People actually think that it was the shadow of the earth that causes moon phases. That's actually incorrect, because if a shadow of the earth crosses the moon, you'd get an eclipse of the moon, a lunar eclipse. It's actually pretty straightforward. So if this is the sun, so if all of this was the sun, right? Now this is the earth. You can see the sun shining full on the earth. Now the moon, it's hiding in the line of sight of the sun. So the sun is still shining on this side of the moon fully, but you don't see anything now because this side is completely dark. But as the moon moves a little bit this way, the sun is shining still half. It's always shining on half of the moon at all times of the month. It will shine on exactly one half of the sun. But as it moves here now, you will see only a crescent, because the moon is moved sufficiently from your vantage angle. The degrees of separation from conjunction is enough for you to now see a crescent. You would see a crescent here. And as it moves the crescent here, you would see a crescent. As it moves, the crescent becomes bigger. So now, even though from the vantage point of the sun, it's now full moon, as it moves, it becomes gibbous, and now you have 3/4 of the moon, and then you have a full moon, And as it carries on around the Earth, it wanes now. The same trigonometry applies. Saying everything is the same until you have a new moon again. Here is the new moon. So full moon and new moon. It's pretty straightforward. Here is another way of looking at it. So if here is the sun, so here is new moon now, right? You don't see anything. So as the moon moves now, it's moved a little bit this way. So you here, anywhere on the Earth, you would see this crescent, slight crescent here. As it moves here, you start to see more and more of the moon. Look, if it's here now, it's this much. If it's here, it's full. And then the same thing happens when it gets back to here again. And then this last one here this is the sidereal and the synodic day we mentioned earlier. So this is how it is, the cycles of the moon. There you can see a perfect cycle, perfection in the order of Allah. Here is a video of the same thing. So here you can see that the moon and the Earth always, really, half of the same side is always going to be illuminated. The same size as in the vantage point from the sun looking upon the Earth and the moon. Always it will be the same, but we don't see it, right? So like for example here now, we'd only see, if that was the Earth, this is full moon. So now the moon is starting to get smaller. We wouldn't see that side. So here, we would only see this much of the moon. So now we'd see less than half. And when we get to here, that's exactly new moon. The sun's shining on the moon, but we only see the dark side of the moon. So now when it grows, we start to see this side here. Crescent gets bigger. Crescent gets bigger until we have full moon, which would be here. I'm sure you get the picture, so we'll move on. Okay, now Luna Anel Emma. This was a picture taken on the May of last year. If you were to take a picture of the sun or the moon at the same position in the sky, with the moon you'd have to actually change, because the moon's position changes by like almost an hour every day. You'd get a picture like this. So this is the orbital plane on the ecliptic of the moon in a whole month. So here you'd have a new moon. So here you don't see nothing here because the moon is invisible. So you'd get the moon growing, growing, and growing, and this would literally where it would be in the sky. And then by the time you have a full moon at the same time of the day, this is where it would be until it goes round again, and there. So these are like time-lapse pictures of days, right? And this would give you this. The sun would also give you that. If we were to play a video of this, this is what it would look like. So this is, again, it cycles through the ages, right? Now remember we mentioned the precession, the nodal precession. You can actually see that here. It's moving through the years, and you can see that. But this is the same motion. We're seeing the same motion. And here you can see, if I pause it, there's the sun. Here's Mars. So in relation to, as we move through our rotational period, you'd see the sun move, different planets move, and that would stay kind of constant in the sky, but it would also move. Why? Because of the precession of the nodes. So for example, here's Mars, and now here's Uranus. And let me just catch the sun. You can see that big thing is the sun, right? So it's as we move around the sun, this is what you would see. Now, eclipses. What are eclipses and how do we understand eclipses? So eclipses only occur when the sun, moon and earth are in alignment, Zai-Ji as they call it. Solar eclipses occur when the moon is between the earth and the sun, and lunar eclipses occur when the earth is in between the sun and the moon. So to understand what an eclipse season is, we need to understand what lines of nodes are. Remember we mentioned the orbital plane of the moon, and there are two nodes where the moon crosses the ecliptic, which is the line of the sun and the earth. Where the moon crosses, you have what's known as an eclipse season. So twice a year you get an eclipse. And due to the regression of the nodes, that changes, because the nodes have a regression that moves, as we described earlier on. So 2 eclipse seasons in less than 1 calendar year, so they're a tropical year. Regression means backward motion. So the earth moves, I think goes eastwards, the nodes regress backwards, westwards. So there's a cycle, and after a certain amount of time, like it comes back upon itself. So it's 19 days earlier, so your eclipse season is 19 days earlier every year. This is the maths behind it. So here is a way to understand it. So if this is the sun and the light coming from the sun, look, full on. This is the earth's shadow. This is the moon's shadow. The orbital plane of the moon is tilted from the ecliptic at 5 degrees. So it's up. It's going to go from here. It's going to descend and then ascend back again. And if the line of node ends up on the ecliptic at the same time here, you'll get a solar eclipse where the moon now eclipses the sun, because it just so happens that the sun and the moon, relative to their size and the distances apart they are from each other, they fit exactly. So even though that moon is infinitely tiny compared to the sun, the sun is so much further away that they both end up being the same size. Subhanallah. And this is a sign from Allah subhanahu wa ta'ala of His creative power, because we know that Rasulullah would get worried when an eclipse happened. Now we don't take omens from eclipses, right? Some people do, the ancient Arabs did, but Muslims don't. Why the Messenger of Allah sallallahu alaihi wasallam would get worried was because it was a huge manifestation of the power of Allah. In our daily lives, we cannot see what's happening in the heavens, and the heavens are huge. And when something happens, the heavens are disturbed, the repercussions for us are severe. So when you get an eclipse, it's a huge event that instantly makes it night. And then you think, oh my God, everything's turned upside down. What's happened? And you realize that really nothing is in your control. It's in Allah's control. Allah made it dark in an instant. You got so used to the sun rising and setting, that you never gave a thought about it. But when an eclipse happens, straight away you realize that your small worth and the infinite majesty of your Lord. So it was a point of worry in the sense that Allah can prolong this. Allah can do more than this. Allah could totally take away the ability for us to live at ease or in safety in the world. So this is why thunder would perturb Rasulullah. He would get worried then as well, because again it's a huge sign. Lightning, when it strikes, it kills people. It devastates crops. We get forest fires due to lightning happening. If it hits a house, it can literally shatter a wooden house. So these are again huge signs. So we don't take Allah's signs for granted and look at them and say, oh wow. We understand the power behind these actions and the infinite power of the Almighty. And it's a point for us again to orientate ourselves back to our Lord and prostrate and worship Him. That's why you will see that there is the prayer of the eclipse. So here you can see that when it's at the top of its ascension, its shadow misses. So we don't get a solar eclipse. Here it aligns, so we get a solar eclipse here. Now the penumbra would be somewhat larger, so you'd get partial eclipses here and a total eclipse here. Here on this side, the Earth's shadow, the moon is out of it, so it wouldn't get an eclipse. Here the moon is inside the Earth's shadow, so you get an eclipse here as well. So the sun makes one complete circuit of the ecliptic in 365 days, so its average angular velocity is 0.99 per day. At this rate, it takes 34.5 days for the sun to cross the 34 wide eclipse zone centered on each node. Because the moon's orbit with respect to the sun has a mean distance of 29.53 days, there will always be 1 and possibly 2 solar eclipses during each 34.5 day interval when the sun passes through the nodes nodal eclipse zone. These time periods are called eclipse seasons. So we have eclipse seasons in a year. The midpoint of each eclipse season is separated by 173 days, right? So we have 2 eclipse seasons, one here and one here, which is the mean time for the sun to travel from one node to the next. The period is a little less than half a calendar year because the lunar nodes slowly regress westwards, as mentioned, by 19.3 degrees per year. The actual value ranges because of the eccentricity of moon and Earth's orbit. So these are the line of nodes. So because the moon is angled, the line of nodes is when it would touch. So when the line of nodes touch the ecliptic, they need to be on the ecliptic. So here you wouldn't get an eclipse here. But because the line of nodes now are on the ecliptic, you'd get an eclipse here. They're on the ecliptic here, but here they're not. So it's unfavorable for eclipse. So during an eclipse, this is what happens. You get the sun and then the moon that comes in between the Earth. And this is the moon's umbra and this is the penumbra. So here you'd get a partial eclipse. Here you'd get a full eclipse. So this spot here is when the sun would be completely blocked and it would become dark. These you would either probably not notice or there'd be a slight dimming depending on how close you are. Here you probably wouldn't even notice what's happened unless you knew it was an eclipse season and you had your instruments out, and you can make small boxes yourselves and you can, like, it's like a camera box. It functions, the light, the light comes into a pin, and then the back of the box it would open up again, and then the crescent would be in reverse and you'd be able to see it. Whereas if you look with your eyesight, it would blind you. This is what an eclipse looks like as it moves across the face of the Earth. So all of that area, North America, would have seen that eclipse. This is an eclipse here again, so as it moves across the sky. So here is eclipse, here is the sun, and then the eclipse starts. Now the moon is moving and slowly going to cover the face of the sun. When it gets to here, you have a full eclipse. Now these are coronal flares that you can see spewing out millions of miles into space from the sun. And then again as it comes out of the eclipse, and here. This is what it looks like. This is it's the annular type of eclipse. So this is actual footage of an eclipse happening. Now because the moon didn't completely fit the sun, it was further away this time. So it left the outline of the sun, and here it comes out. Here it would not be it's a complete eclipse, but it's called annular in the sense that you'd get the sun visible here, and that would still give you sufficient light. So we have 3 types of eclipses. We have a total eclipse, which is when the moon appears the same size as the sun and blocks the light. We have an annular eclipse in which the moon passes between the sun and the earth, but because of the relative distances of each, it appears slightly smaller. Then you have a partial eclipse, which is part of the moon crosses the sun. So this is how it looks like: a total eclipse, annular eclipse, and a partial eclipse. This is how the science works. This is a partial eclipse, this is a total eclipse, this is an annular eclipse. In an annular eclipse, this is what you would see. In a total eclipse, it totally covers the sun's solar disk perfectly. It becomes dark, and these are huge, raging solar flares spewing out from the surface of the sun. And these are like part of the corona, you can see. This is a time-lapse video of an eclipse. SubhanAllah, it's a sight to behold. This is sped up. It would take hours for this to happen. This is sped up. And then here you'd get what they call the diamond ring now. So as praise be to the Lord. If you want, you can get from this website, you can get all the data of when the Saros eclipses happen, the eclipse seasons, and you can follow them. This data does take, you need to know how to interpret it, but once you do, you'll easily know what Saros series you are, the nodes, the dates, and the type of eclipse you can see around the world. You can get this data on these websites. So this is how it would work. The eclipse limit, partial or center, it's to do with the size of the sun and the moon, how close the moon is to our Earth, and determining the size of the eclipse and how far away it would be to determine a full one. Eclipse maps, you can again download the eclipse maps that show you how the eclipse would move through the Earth and their dates as well. These are total eclipses, and then the annulars would be on their side. So when you have a total, you have a slight. Oh, sorry. Yeah, these are total eclipses, and then the annular eclipses, which are when the moon is closer. So as the moon enters the umbra, it becomes red here. Here, it would just get eclipsed. So here, for example, here's a total. It starts at 9:33, and the end of the partial is at just over 1 hour. So it's 1 hour 10 minutes. The mid eclipse is 2 hours, 1 hour 45 minutes from there, and then the partial ends here. So it goes on for a few hours. So you can see how now the moon would be entering the Earth's penumbra here. When it enters the umbra, it becomes blood red, and then it comes out, you get partial, and then it's totally out. Here's a video of what it would look like. This is time lapse. This is what you would see. So it's entered the penumbra now. That you will see a slight darkening, but you won't see much difference. But the minute it enters the umbra, it's a different story altogether. So this is an animated map of how the eclipse travels across the world and where it's visible from. Again, from the same website, it's the same thing, how it would be visible on the Earth. So this is now a lunar eclipse. We saw a solar eclipse. Now let's have a look at a lunar eclipse. So here is the eclipse starting. So if I forward it, there's your beautiful blood red moon. And then as it comes out of the umbra, back into the penumbra, this is what you see. And this is what it would look like here. So it's being eclipsed by the penumbra, and then as it enters the umbra, beautiful golden color, and then it comes out again. This is an actual shot. This is the moon as it enters the penumbra. Totality has begun now, and then totality ends, and then the partial starts in the penumbral stage, and then that will end after 45 or 50 minutes. So the moon turns red, as mentioned before. It's to do with the shorter wavelengths being scattered by the atmosphere, and the longer wavelengths get through to the sun. Metonic cycle we'll touch upon in the other video on lunar solar calendars. Thank you for watching this video. It was a lot to take in. Inshallah, we learned a lot in this video, and there will be a second video on intercalation of how certain religious groups such as the Jews, the Chinese, the pre-Islamic Arabs used to intercalate, which is adding months or adding days into the lunar calendar, and it would be months, right, if it was going to be the solar calendar, to bring their calendars back in line with their religious or economic activities. So then after that, inshallah, we'll finally in part 3 have a look at the fiqh of moon sighting, of how actually to observe the moon, when's the best time, where to see it, what do you need to observe the moon. Then in part 3 we'll have a look at the fiqh of moon sighting, how to actually sight the moon, right? What's the best way to sight the moon, what are the procedures involved, and whether we can have calculations, whether it's global sighting or it's local sighting, and then the evidences to support each case. So thank you very much for this, and inshallah see you next time. Assalamu alaikum wa rahmatullah.